Hey guys, welcome back. Where I left off last, I showed you a number of derivations to find out what the moment of inertia was using integral calculus. Now I'm going to do one that was a free response problem, and it's also going to go into driving the period of a different thing in the same way. So, looking at our picture here, move this down a little bit so it's out of glare. We have a uniform rod of mass M and length L. It's pivoted at a point that's a distance L over 3 from the top end as shown above. The rod is pulled back so that it makes a small angle with the vertical and then is released. Using integral calculus, show the rotational inertia for the rod about its pivot is ml squared over 9. So I could do this easily with the parallel axis theorem, but they're asking us to use integral calculus. So I'm going to use integral calculus. So I'm going to start with what my formula is, and my formula is that my moment of inertia is going to be the integral of r squared times dm. And again, I have a variable and a derivative that aren't the same, so I have to relate it to what it is. They're telling me that it's uniform. These are always going to be uniform, and so that means that I can relate dm to the total mass as I would relate dr to the total length. Or if you want to do dx to the total length, we have r squared in our integral, so it might be easier to do dr. So I'm going to solve for dm and substitute it in over here. And I'm going to take out the m over L because that is a constant, and that's going to be the integral of r squared dr. Now, I need to go from, this was going to be our pivot point, so this is going to be 0. And so I'm going to go from negative L over 3 to 2/3 L. And you could just as easily go from negative 2/3 L over 3 to L over 3. It wouldn't make a difference. All right, so now when I do this, I'm going to get M over L. I'm going to have r cubed over 3, and this is going to be from negative L over 3 to 2/3 over L. All right, so I'm going to have M over L times 2 cubed is 8. 3 cubed is 27. 27 times 3 is 81. So I'm going to have 8L cubed over 81 minus negative L cubed is going to be negative L cubed. Over 3 cubed, which we said was 27, times 3, which is going to be 81. And so I'm going to have 8L cubed plus L cubed, and they're both over 81, so that's going to be 9L cubed over 81, M over L. And if I do a little simplification, I can cancel out 1L, and then I can cancel out a 9. And so I get ML squared over 9. And so they're going to want to see every step because you can use the parallel axis theorem to do this more simply. And that's why I stopped the video, because I felt like this was a lot. This is just part A, right? All right, using Newton's second law in rotational form, write but do not solve a differential equation in terms of M, L, and physical constants as appropriate. that can be used to determine the angular displacement theta as a function of time t. Okay, so here is our diagram of what is going on here, and it's going to pivot about this axis that's 1/3 up. So that's going to be theta in there. So the second law for rotation. Let's look at the second law for linear and go from there. So if you remember, this is F net equals ma. This is applying the second law to something that's accelerating linearly. We're interested in rotation. So this is, instead of F net, your equation sheet says it's the sum of the torques is equal to I alpha. Well, we just found out that I is ml squared over 9. We can rewrite our torque as the vector cross product of our radius and our force. So what force is going to make this go back and forth? That force is going to be the component of the weight. And so at the center of mass, there is the force of weight that is going straight down. And we're interested in the part that's perpendicular. That's what this means. So vector cross products combine perpendicular components, and you end up with a vector afterwards. All right, so I need to know how far I am from there to there. Well, I know that the pivot is L over 3 from there, and I would consider the center of mass of a uniform block to be L over 2. So our distance from the axis is going to be L over 2 minus L over 3. And so this is going to be, the common denominator would be 6. So 3L over 6 minus 2L over 6 is L over 6. And then to combine the perpendicular component, that's going to be mg sine of theta. All right, so in all of these, when we did our angular displacement ones, we made an assumption. We said that for small angles, that theta is approximately sine of theta. So even though that I know that this is L over 6 times mg sine of theta, and it's a negative because it's a restoring, I'm going to just put in theta. So I have minus L over 6 mg theta equals I alpha. All right, so not quite a differential setup yet, but I'm going to make it one, and I'm going to do this by expressing my angular acceleration as the second derivative of the angular displacement with respect to time. So this is going to be minus L over 6 mg theta is equal to I, which is m L squared over 9, the second derivative of the angular displacement with respect to time. And you could also write this in that form or in that form. All right, can I clean this up at all? Yeah, I can. I don't have to. They'd have to accept it and to simplify it. But Let's get rid of an M. Let's get rid of an L. Let's take the 9 to the other side. So it would be 9/6, which is going to be 3/2. So I'm going to have negative 3/2 G theta is equal to, why don't I get the L over here too, so we have everything else on the side. So I'm going to have 3/2 G over L theta. And on the other side, we're just going to have the second derivative of the angular displacement with respect to time. All right. Using differential equation from part B, show that the period of oscillation for the rod is given by the expression T equals 2 pi square root of 2L over 3G. So I did this for a pendulum for you guys in class, and I did it for a spring for you guys. And I'm going to do it for a hula hoop for the lab that's coming up and a meter stick. So looking at this, make sure I have it written down right. I have minus 3/2 G over L theta is equal to the second derivative of theta with respect to time. All right, so this is simple harmonic motion. And so I can say that theta is equal to A cosine of omega t. And again, remember, this omega is our angular frequency, not our angular velocity. So this is going to be 2 pi over the period, which is on our equation sheet. This is important because if we look at what our answer is, this is where we're going to get the 2 pi and the t out of here. All right, so let's get what the second derivative of this is with respect to time. So the first derivative is going to be negative A omega sine omega t. And the second derivative is going to be minus A omega squared cosine omega t. And let's plug in these for theta and the second derivative of theta. So I'm going to have minus 3/2 G over L. Let me move this over. Make sure I have enough room. So minus 3/2 G over L A cosine omega t is equal to negative A omega squared cosine omega t. Can I cancel stuff out? Yeah, always. And that's the benefit of this substitution. And so I'm going to get rid of my cosine omega t and my A and my negative. So this tells me that the amplitude doesn't matter. As long as it's a small angle, the period's not going to be affected. And that's what we saw with pendulums and with mass springs. It didn't matter at all what the amplitude was. You could have a big amplitude. All right, and for omega, I'm going to plug in 2 pi over t. So now I have 3/2 G over L is equal to 2 pi over t squared. So I want to get t to the other side. So I'm going to have t squared over here. And then I'm going to get this stuff to the other side. So I'm going to have 2/3 L over G. And I'm going to have my 2 pi squared. And then I'm going to square root both sides. So I'm going to end up with 2 pi square root of 2L over 3G. And once you know, that is what the answer is. An experiment is performed with the thin uniform metal rods of different lengths, each pivoted around a point 1/3 the length of the rod from the top end and used as physical pendulum, as shown in the figure of the previous page. Each rod is pulled back so that it makes a small angle, which is our approximation while we could get rid of sine of theta and just put theta in. The vertical is then released and the period of oscillation is measured. The data are recorded in the table below. Indicated how the quantities should be graphed to yield a straight line whose slope could be used to calculate a numerical value for the acceleration due to gravity. Use the remaining rows in the table above as needed to record any quantities. All right, so going back to our equation, we said that T is equal to 2 pi square root of 2/3 L over G, right? Just want to make sure. Yeah. All right, so if I want my slope to be G, I need to solve my equation for G. So I'm going to square both sides. I'm going to write it as capital G, capital L, because that's what they did. And I'm going to get G by itself. So I'm going to have G is equal to 2L over 4 pi squared. So I could write that as 8 pi squared, right? And it's 8 pi squared L over 3 T squared. And then I can either graph this whole thing as my y-axis and this whole thing as my x-axis, or I can just graph L and T squared. And because it's a constant, right? 8 pi squared over 3 is going to be a constant. So I'm going to do 8 pi squared L. That's going to be in meters. And I'm going to do 3t squared, and that's going to be in seconds squared. So we need to write what it is, and we also need to write what the units are. So let me crunch these out. So 39.5. $79. $118. $158. And $197. And then 3t squared, I have 4.3. I wouldn't worry too much about putting a bunch of decimals on here, because you're not going to be able to graph with that kind of precision anyways when you graph it. I'm guessing that's the next page is going to be. So wherein lies the struggle? Well, knowing how to do all this stuff is a little bit, but the other one's a time one, right? Like we're saying that this should happen in 15 minutes for any of these. Even if you didn't know the calculus parts, or you only knew parts of the calculus parts, you should be able to put an answer in here that would be because they give you what the equation is. So just because you don't know how to do part A or part B or part B2 doesn't mean you can't do part C and still get some points. All right, I'm going to take a picture of this data. Go on to the next slide. All right, plot the straight line data points on the graph below, clearly scale and label. All right, so my vertical axis is 3t squared. This is going to be second squared. This is going to be 8 pi squared L. This is going to be, oh, I have that backwards. I cut that part off of the picture. We're looking at 8 pi squared L is meters, and we have 3t squared is second squared. All right, so 3t squared goes up to 20, so 5, 10, 15, 20. Don't write every line. Every fifth one's bold. Our length goes from 0 to 200. I have 1, 2, 3, 4, 5. So I could make them 40. I'm just going to make them 50. So I'm still using most of the graph, but I'm making it the easiest divisions for myself. All right, so I'm going to plot it. And I have 4.3 and 40. I have 7.7 and almost 80. I have 12 and almost 120. I have 16 and almost 160. You can see how easy they made the numbers. And 20 and almost 200. Very linear. All right, now they want us to solve for G. I'm going to do a best fit line, and then I'm going to pick 2 points off of my line that aren't my points that are far apart. And I'm going to make it very clear what those 2 points are. So that's my best fit line. Yours should be better because you're probably using a ruler. And I'm going to say that it crosses right there. So I'm circling those. And right there. And so my first point is going to be 4, 40. And my second point is going to be 20, 200. And then G is going to be my slope. And so on the y-axis, I have 200 minus 40. This is in meters. I need to have the units there. And I'm going to have 20 minus 4. That's going to be second squared. So I have 160 over 16, which is going to give me 10. Which I looked up with those 2 points. I always circle the points I'm using, and I didn't use the value for that one, so that one's not on the line. So the idea is that all of your data together is better than any of your individual data. So if you were to find out what the gravity was from each individual point and find the average, this is going to be better because this will, if you have one that's out of whack, when you do your best fit line, you won't have to worry about it.